Hello, my name is Junho, and I'd like to introduce our work named MasKGrasp. I'd like to start with some demonstration videos of our grasping algorithm. Our algorithm can distinguish instances of both opaque objects and transparent objects, and grasp objects of various shape and texture. As in the video, we propose a real-world grasping algorithm with two key characteristics. First, we want to be able to grasp both transparent and opaque objects as seen in the picture on the right. Given an image observation, we first detect instance masks. Then we calculate pixel-wise grasp affordance maps called QMaps. Second, we further improve the grasp success rate by learning to avoid clutter. For a scene such as the image given on the right, we want to avoid grasping where two objects are in contact, indicated in white. Our QMaps consider the relative positions and predicts low grasp success rates, shown in blue, for cluttered regions. Most existing grasping algorithms are implicitly tailored to opaque objects, and they fail for transparent objects. This is because it is very difficult to get stable measurements due to the different physical properties of transparent objects. The figure from ClearGrasp best illustrates this phenomenon. The measurements of depth sensors are based on a ray reflected from the surface of an object. But for transparent objects, some rays pass through the object and result in inaccurate depth values. Comparing the depth images of scenes with opaque objects and transparent objects, you can see the effects of this phenomenon. Thus, in order to grasp both transparent and opaque objects, special attention is required. Being able to perceive transparent objects is important, as many transparent objects exist around us, ranging from glass kitchenware to laboratory equipment, especially for applications such as lab assistants and household robots. Manipulating transparent objects is crucial. Our network for grasping consists of two parts. The first is detection network F, which detects graspable objects within the scene in the form of object masks. Out of the detected masks, we select K objects as input to the subsequent network. The grasp estimation network, G, observes these K masks and selects the best grasp with the highest possibility using the QMap and theta map. We will introduce networks in more detail in the following slides. The detection network F takes as input a single image I and finds n instance masks of graspable objects within the scene. The challenge here is to obtain stable performance for both opaque and transparent objects. Large-scale real-world datasets, such as MasKGrasp, is biased towards opaque objects, with only scarce wine glasses as examples of transparent objects. To tackle this issue, we synthetically augment each image in MasKGrasp with transparent objects using pre-calculated flow. For example, we can combine an image with a single laptop with multiple transparent objects and transform it into an image with 4 objects, 3 of them being transparent. Trained on this dataset, our detection network successfully predicts instance masks from our real-world environment. After obtaining the instance masks, the grasp estimation network, G, observes the top K masks and predicts a global QMap with pixel-wise affordance of grasp. The red pixels of the QMap indicate grasp positions with high success probability and blue otherwise. In addition, we also predict a theta map, which contains pixel-wise optimal grasp angles. From these two maps, we can compute the grasp by selecting the highest QMap pixel and reading the theta map at the corresponding pixel. The resulting grasp is the red rectangle on the rightmost image. Our grasp is also designed to avoid cluttered regions, as you see in the picture. This strategy stems from the intuition that the success rates increases when the robot grasps where objects are not cluttered. Clutter avoidance is implemented by simultaneously considering the relative position of multiple instance masks. Our grasp estimation network jointly considers the masks and finds the overlapping regions for every pair of detected objects. For example, in this image, the region of clutter for the two instances is indicated in magenta. The combined global QMAP contains low values for these regions of clutter. We experiment our model in the real world with a Panda Franco robot. The picture on the right shows an example of our grasping environment. In our paper, we report the success rates of our model in various configurations. We test with objects of varying complexity, shape, and texture, and mix transparent objects with opaque objects. The objects we use for our grasping tasks are shown here. These are the summary of our experiment results. From the top table, we can see that our algorithm performs better on average while being more stable. The values are the mean and standard deviations of the success rates of 4 configurations with 13 trials each. The second table illustrates the effectiveness of clutter avoidance. With clutter avoidance, the success rates dramatically increases for scenes containing objects with at least one edge in contact with other objects. We suggested MasKGrasp, a grasping algorithm extendable to both transparent and opaque objects. Using masks and clutter avoidance, we maximize the grasp success probability. However, MasKGrasp is a grasping algorithm that works in 2D space with a fixed grasping height. We aim to use multiple views to expand this work into 3D space to allow higher dimension grasping in diverse configurations. Thank you for your attention.